Asking, yes, asking again to join. Okay, so as we were discussing about previous class, today's class we are going to study calculus of variation, students. So brief idea about why we study the calculus of variation and why it is important. So just see that calculus of variation here, students, it is a powerful technique for solution of problems. Yes, as I told you that mathematics is a very powerful technique to solve the problems. That is very important. I always tell that mathematics is there to solve the any type of problem. There is a solution for problem. That is what mathematics says. It says that for every problem there is a alternate solution. Alternate, you have an option, right? So here also this is also a powerful technique for solutions of problems in dynamics of rigid bodies. Yes, optimization of orbits and vibration problems. So this is all we are going to deal with. The subject primarily concerns with finding maximum or minimum value of definite integral involving a certain functions. Yes, students, you can just see this is a maximum and minimum value we are going to find using a simple integration, right? I will tell you what simple integration we will be using. Also, it is something beyond finding the stationary value of a given function. Only an elementary exposition of the subject is given here with the sole aim of introducing the students to a topic whose importance is fast growing in science and engineering. Nowadays, you can just see calculus of variation is very fast and growing in science and technology, students. So first here, what this is just a brief idea about calculus of variation. First, we will be studying what is a functional. Suppose if you take a problem of finding a curve, right? Whenever you want to find any curve, so how you going to find by using the functional? Suppose if you take the x-axis and y-axis here, friends, you can take any curve like this. Okay, so now what you do? Yes, you take a point, this point A as x1, y1, and this is a point B, x2, y2. Then whose minimum length we are going to take? So minimum length I will take this, right? Then I take this curve as y is equal to y of x. So this is how we are going to calculate the curve, and we will just see what is the length. We'll discuss what is the area, how much is the covered this area, right? All these things we are going to study in the calculus of variation. As well as you should remember that this from A to B, maxima is there and minima is there. This is minima and this is you are going to get maxima. So here the function will be different, and here we have taken y is equal to y of x. Here you can take the function as y is equal to y of x plus this is some extra, right? A to B, this function is minimum, so minimum must be there. With that, what is maximum? This is extra part, that is epsilon nu of x. So this is what we just say, this is extra part. This is what extra part, you can just see this part we say, right? So therefore we take this two curves and we see this is a functional, or you can just take this as function of square root 1 plus y dash square, right? And then we find the area covered by this curve. How you find the area covered by this curve? You go on adding the strips here, one strips. Already we have seen in the numerical methods, we take the always strips here, right? The small strips. So we add all together, you will get the integration from x1 to x2. So this point we will be taking x1, and this we are going to take this as x2. So whatever the area covered from x1 to x2 will be finding with the help of integration, students. Okay, so this is all you have to know. So all more theoretical part is there. Okay, so here we have the same curve. So in general terms, we We wish to find the curve y is equal to y of x, where y of x1 is equal to y1. Yes, we are going to take this y of x1 is equal to y1, and y of x2 is equal to y2, such that for a given function f of x, y dash. Yes, students, we till now we have just seen f of xy was the function, right? But here we are going to involve, here there is one another value, that is y dash we are going to take, because this is a calculus part. So differentiation we are going to involve in this. So the function contains the calculus, that is differentiation y dash, and this is what we say, it is a stationary value or extremum value, students. Okay, so an integral such as we have seen in the equation defines the value for the function of the type y is equal to y of x, which is a curve, which is known as functional. Yes, students, we'll just take this as the our functional. So this is all about the functional. What is functional? What is the curve, how we are going to take, and what all the things we have to remember for the curve. 2 points, two curves we have, minimum length we have one curve, and maxima we have another function. So these all things you have to remember while solving the problem. This all things are important, friends. Okay, so yes, this is all about the, okay, then we'll first derive the first derivation here, that is Euler's equation. Yes, very very important, students. So very few questions are there here, as well as all the questions are very very important. Only thing you have to practice this derivation, or we just take this as not as example, but we say Euler's equation. So please write down what you have to remember. Euler's equation derivation, you should remember. Yes, here again integration we don't substitute everything, because this is derivation, means we'll be writing the statement here. So please write down the statement. A necessary condition for integral, I'm going to consider this as I, it is denoted by I, integral from x1 to x2. The function here we are going to take, that is f of x, y dash, that we have already discussed, to be and extremum. That is, you will get this as dou f upon dou y minus d upon dx dou f upon dou y dash is equal to 0. This is called Euler's equation. Okay, students. So like this, you should remember what is the function we are going to use, and what we are going to prove here. So this is Euler's condition. We'll just see the necessary condition here. Okay, so we can just prove this. I'll write proof only. Proof of this. So please remember the proof, student. This is very very important. Okay. So whenever they give the any function here, this I is equal to integration x1 to x2 f of x, y dash. Okay, here we will be explaining this first, and then we will arrive to this answer. Okay, so we'll just start with our as usual the function now. Remember the functional definition. We take the curve y is equal to y of x be the curve, right? And for this function, we have this graph, but here again this graph I will take. Okay, so you have to draw this graph here. So joining the points a of x1 y1, b of x2 y2, which makes integration, that is I, function extremum. Right, this is all we are using the definition of functional. Now as I told you that from a to b we have one curve, that is y is equal to f of x, which is the length, right? And we have another curve, that is this curve. We have y is equal to y of x plus epsilon no of x. So we'll describe again this curve also. Okay, so we'll take again, let y is equal to y of x plus epsilon mu of x. Okay, again be the curve, same things. So here you can see this. I will take here nu of x1 is equal to, here at this point, at point A, where is it point A? At point A, if you take the nu of x1, students, please see, yes, this is, I already told you, this is, you will get this as x1, and at this point you will get this as x2, right? So this part you are going to calculate actually. This you are going to calculate this upper part, right? But at this point, nu of x1 will be 0 because it's starting point, and here at the end point, the both the curves meet. So this extra part, whatever we have taken, that is nu as extra part. This is the extra part. Suppose if you take this line and this line, right? So this is extra part is new. That is extra. It is coming outside, right? So this part nu of x1 will be 0 at point A. So this is 0 at point A, and nu of x2 is equal to 0 at point B. So therefore you have to keep this in mind. Then we will take the value now. After describing this, we are going to take the function. Now for this value y is equal to y of x, you already seen the function here, integration x1 x2 f of x y dash dx. But now for this curve y is equal to y of x plus epsilon nu of x, for this we will write the function here. Yes, so x remains as it is. I can just see here, mm, this point. Okay, x remains as it is, no change in x, only y value is changing, right? Only this y will change from this point to this point. So therefore we will write the function here. So please remember, for this curve y is equal to y of x plus epsilon nu of x curve, we are going to write the function or value of I along, we'll take the equation 1. So where is the equation 1 we will choose? We will take this equation 1. For this curve we will write the value is I is equal to, as usual, x1 to x2, students, curve is from x1 to x2 only, right? So now the function is x, no change, x value they have not given, only y value is changing. What is y value is changing? That is y of x plus epsilon mu of x, right? And for y dash, just differentiating this, runs, actually this is differentiation, or the another term, that is calculus we are taking here. So if you differentiate this, this will be y dash of x plus epsilon mu dash of x, right? So this is dx. By definition of functional, students, what is functional definition? Already we have seen here. There is that here, integration x1 to x2 f of x y dash, means whatever y is here, we are differentiating this y dash, that's it. So by using that we get this integration I is equal to, is it clear? So now we see we see the conditions here, students. So as this epsilon is a function, right, being a function of epsilon, so maximum or minimum value, we have seen the maximum or minimum value we have seen, that is epsilon will become 0. So for epsilon is equal to 0. When epsilon is 0, students, please remember that when you differentiate this with respect to epsilon, automatically this term will become 0 at epsilon is equal to 0. So this condition we are using in this to get the Euler's equation. Okay, please remember we want to get the Euler's equation. Yes, we can just see here they have differentiated this. So therefore we also differentiate now this. So differentiating I under the integral sign. So we will use here Leibniz rule, students. Okay, this is Leibniz rule we will take here. So therefore I will just differentiate this di upon d epsilon, which is equal to, yes, so this is equal to integration. When the differentiation we have taken in the integration sign, inside the integration sign, differentiation, ordinary differentiation will be written in terms of partial differentiation. Please remember this. Okay, so because here we have more than one independent variable, x is there, y is there, y dash is there. So therefore there are more than one independent variable, but we want here only one independent variable. Therefore we use this. Okay, so now we will simplify. So there are again three functions, x, y, y dash. Okay, so one by one we will simplify this. So I will take this as dou f upon, we are differentiating with respect to epsilon, right? So this is a function with respect to x, and then we have y, and then we have y dash. But see, when we are going to use the partial fraction, we will take with respect to x here, so that when we differentiate this x with respect to epsilon, so just I will be taking dou f upon dou y. Instead of dou f upon dou y, I just multiply here dou x divided by dou y. Okay, so this is again plus dou f upon dou y into dou y upon dou epsilon, plus here it will be y dash function is there. So dou f upon will differentiate with y dash into dou y dash upon dou epsilon, friends. Why we have taken this one? So see, I can apply this condition so that we can simplify this problem very easily. Okay, so now we can see here epsilon being independent. Yes, it is independent, students. So it is independent of x. Therefore, wherever dou x upon dou epsilon is there is going to become 0. Yes, students, this first part will become 0. So please keep this in your mind, students. And also dou y upon dou epsilon will tend to nu of x, and dou y dash upon epsilon will become nu dash upon x, means it is going to tend towards nu of x and nu dash of x. So these three things you have to remember. Now I will substitute in this formula. So this part I will be substituting. So these are all conditions we are going to substitute here. So therefore this is di upon d epsilon is equal to integral x1 to x2. First term is 0. I will leave this, right? Now here dou y upon dou epsilon is going to become nu of x, that I will write. This term is 0, students. This term is nu of x, I will substitute, and this term will become nu dash of x. So therefore I will write like this: dou f upon dou y nu of x plus dou f upon dou y dash nu dash of x dx runs. Now we will integrate this, but before integrating we know this part, so we'll just take this as, that is, integration from x1 to x2 dou f upon dou y nu of x, so which will give you actually dou f upon dou y, because your integration is between for x only, right? So this nu of x is again very small quantity, therefore only dou f upon dou y we are going to substitute. Okay, so I will keep this integration for this x1 x2 dou f upon dou y nu of x d of x, as it is I will substitute here. Here this quantity is different, so integration plus integration x1 to x2, I will just integrate this part. There is second part I will be integrating nu dash of x d of x. Okay, students, so we know that we can just take this as direct value. I will substitute. This is equal to dou f upon dou y. Only this part is remaining. Okay, so therefore this is plus. I will integrate this runs. Integration by parts. This is u and v. I will take one by one. I will integrate. Yes, I will keep dou f upon dou y dash as it is. Integration nu dash, again differentiation is there here, so this dash and integration will get cancelled, therefore differentiation it will become normal nu of x. So therefore I will write here nu of x under the integral sign x1 to x2. Okay, minus, so now I will integrate this x1 to x2 and differentiate u, that is per, you can see differentiation integration by parts we are doing, so differentiation of this will become dou upon dou x d upon dx dou f upon dou y dash. Okay, and then nu of dash x integration again we are going to do, so again nu of x will remain right in the integral sign. So now we will simplify this one by one. Okay, here this is equal to dou f upon dou y is remaining. Yes, so I will simplify this inside this bracket. Dou f upon dou y is remaining, and d upon dx dou f upon dou y dash nu of x, right? So therefore from this part, okay, if you simplify this, you will be getting this as integration x1 to x2 dou f upon dou y minus d upon dx dou f upon dou y dash nu of x1. So you can just simplify this dx. So nu of x will be constant. So integration will take lot of time. So therefore you please remember this step. Then we say since this has to be 0, students. So please remember Euler's equation, that dou f upon dou y minus d upon dx dou f upon dou y dash is equal to 0, which is known as Euler's equation. So this much is enough, friends. If you integrate this, it will take lot of time. Therefore, we'll be taking only the part, this part, which will be equal to 0. So how this is 0? What Euler says, Yes, if you take the necessary condition I is equal to integration x1 to x2 f of x y dash dx to be an extremum, this value must be equal to 0. So we are not going to integrate this, student. So please remember this integration, we are not going to integrate completely. So only for our derivation, what is that? This part we wanted to show equal to 0. So this integration will definitely, if you simplify step by step, not necessary, which will give you this part. There's integration x1 to x2, dou f upon dou y minus d upon dx, dou f upon dou y dash, mu of x is equal to dx is given. Since this is equal to 0, so dou f upon dou y, only this part will be equal to 0, which is known as our Euler's equation, student. So please remember, so quite easiest derivation this is. I'll just repeat same. We know the function integration I is equal to integration x1 to x2 f of x y dash dx. This is from definition of functional, right? What Euler says, this term is equal to 0 in the integral sign, this term is equal to 0. That is what we have to find. So these functions may be any curve is there which is will be equal to 0, right? Or it may be any circle is there, right? All the functions under the curve we are going to take this equal to 0. That is what Euler says. And here the how many values are there, how many function, this function will be for x, y and y dash. So please remember this three. Then we just take the curve, one curve we will take, y is equal to y of x. Then for this curve, this is extremum. So therefore we take this a point A and B, and we take this length y is equal to y of x. Then we take another curve y is equal to y of x plus epsilon nu of x. So under this curve we are going to find what we are intention is, we are going to find this, yes, how much it is covered, what is the area, and all we are going to discuss in the examples. We'll just discuss this. So to find this, we again take these strips, right? One by one we take these strips and we go on adding them. We will get the integral sign from x1 to x2. So this function is, so the curve at point A, what you have to remember from the graph, at point A, nu of x1 is equal to 0 because it is the starting point. Both the curve meet at this point. So therefore this is 0. So there is no gap between them. And then at point B, nu of x2 is equal to 0. So there is again no gap is there. Therefore this extra part is not there. Okay. So keeping this in mind, we take the integral sign for these two curves. Right. Now I is equal to integration x1 to x2. For this curve y is equal to y of x, we know already the function is x y y dash. So this is just differentiation of y. Huh? Please remember y dash is just differentiation of y. Okay, so for this curve we know the function here. Now for this curve you should know the function that this y is going to be y is equal to y of x plus epsilon nu x. So that we are going to put here. So x remains as it is. Here you will get plus epsilon nu of x. Okay, differentiate this y dash, you will get y dash. So this is y dash of x plus epsilon nu dash of x. So here we get the function. That is what I have written in the integral sign from x1 to x2, because all these strips we are going to take, all we are going to sum up them. So therefore we use the integration. Okay, students. Now again from the figure, whatever this epsilon is there, what is the extra part, what we say, or some value we are going to add to the function, right? This is 0 when the integral is, when you differentiate this, di upon d epsilon will be become 0 at epsilon is equal to 0. So now we'll just differentiate this I integration, then you can easily find this is x terms are there, here y is there and y dash is there. Then we will add them. You can simplify. The first part is 0 because epsilon is independent, right? Therefore d upon d epsilon is 0, so dou x upon dou epsilon will become 0. Then this dou y upon dou epsilon is an extra part, therefore we take this as nu of x. And dou y dash upon dou epsilon, we are going to take nu dash of x. So just simplify, you will get this integration. So if you want, you can just integrate this and substitute the values, not required. But you remember, whatever the integral sign, inside this integral sign, if you simplify this, you are going to get this step: integration x1 to x2, dou f upon dou y minus d upon dx, dou f upon dou y dash nu of x dx. So what we require from the Eulers is this one, this part we are going to take. That is dou f upon dou y minus d upon dx, dou f upon dou y dash. It says that this is tends to 0, which is known as Euler's equation, student. So this will be helpful for solving the example. So please practice this derivation. Then we have again some solutions of Euler's equation is given here. So you can just see every solution of Euler's equation which satisfies the boundary condition is called an extremal, students, okay, or the stationary functions of problem. The extremal can easily be obtained in the following cases. So what it says, what we have derived here, Euler's equation, that is dou f upon dou y minus d upon dx, dou f upon dou y dash is equal to 0. This is the first formula you have to remember to solve the example, students. By using this only we can solve the different types of examples we are going to solve. Okay, so for this, he says, if you take the boundary condition, then this we were going to get extremal or stationary functions of problem. So extremal can be easily obtained in the following three cases. So please remember, again there are three cases are there. As we have seen in this function, that this function is defined, where is this? Yes, integration x1 to x2 f of x y y dash. This is a stationary or extremum, right? So for this three, we have again three conditions. So you are going to note it here. When f is independent of x, means dou f upon dou x is equal to 0 if you get in the problem, then Euler's equation, you are going to differentiate this f minus y dash dou f upon dou y dash is equal to 0. Directly we take this and simplify the problem. Then next step is what? Just integrate. You see this d upon dx will go. Okay, so this is equal to constant. Therefore, this directly gives the solution of Euler's equation. So this is a direct method, friends. You can just see when f is independent of x, means in short, इसमें क्या है d upon dx में कोई भी x value नहीं रहेगा. There is no x value inside this, right? Then we take it directly that looking at the question only we can just see f is independent of x. Directly integrate the students, you will get the direct answer, or you will get the direct solution of Euler's equation. So please remember this case, we are using this for the solving the problem. Okay, so next what you have to remember, yes, this you remember, when f is independent of y. Yes, students, if f is independent of y means f is not there, or dou f upon dou y is equal to 0 we are getting, right? At that time Euler's equation is reduced to d upon dx, dou f upon dou y dash is equal to 0. So differentiate only dou f upon dou y dash term here, students. So please remember, when it is x, we differentiate f minus y dash, dou f upon dou y dash is equal to 0. If it is y is independent, then we just differentiate dou f upon dou y dash is equal to 0. Then integrate this, you will get dou f upon dou y dash is equal to some constant, students. Okay. So when f is independent of y dash, yeah, this is little bit change. Means f is independent of y dash means what, students? Dou f upon dou y dash is equal to 0. So 0 cannot be the solution, right? So there must be some solution. Therefore, we take dou f upon dou y dash is equal to 0. The equation 1 or Euler's equation will become dou f upon dou y is equal to 0. which gives the direct solution. Or we just take integrate this and you simplify the problem, students. Suppose if f is independent of x and y, this one condition, one example we have on this, that is when f is independent of x and y means f is independent of x and y means what, student? Dou f upon dou y is equal to 0, dou f upon dou y, x is also 0. So dou f upon dou x is 0, dou f upon dou y is equal to 0 means if any function is given, if you just differentiate partially with respect to x and with respect to y, the answer you are getting here is 0. So what you are going to do, you are going to use this condition, that is y double dash dou square f upon dou y dash 2 y dash square is equal to 0 means even if dou square f upon dou x dou y dash is 0, dou square f upon dou y dash is equal to 0, then we are left with the last formula, that is y double dash dou square f upon dou y dash is equal to 0. Then what you take, dou square f upon dou y dash square is not equal to 0. It is reduced to y double dash is equal to 0 means you are going to integrate this so that the differentiation will go, y double dash will be equal to 0, which gives the solution of the form y is equal to ax plus b. So this all theory part you have to remember, students, and remember the your condition, for which condition which formula you are going to use. So today's class we are just studied Euler's equation, derivation of Euler's equation, and this condition, students. Is it clear? So we will continue in the same discussion in the next